You can all cheat and just read it. Or not.
Electrons are transferred from one species to another.
Electrons transfer from one species to another. Electro means, sounds like? Electrons. What happens when we do chemistry? We do reactions. So what is an electrochemical reaction? Electrons. Reactions. Exciting, right? That's what it means. The name breaks it down for you. To go through and look at electrochemical reactions, though, we have to be aware of the electrons. Okay? So that comes in with this kind of nebulous concept of oxidation numbers, which I think gets brutally, couldn't come up with a good word for that, so I lost it. Not very well presented, because oxidation numbers oftentimes appear like charges. They're entirely different things. Where do you find a charge? Top right. So everything we write out for chemistry, the charge is given to you every single time. It's in the upper right-hand corner. Where's the oxidation number written? It's not. It's never given to you explicitly. The oxidation number is something that must be calculated. How do we calculate it? We take advantage of the charge. Okay, so we'll use the charge to help us interpret it. The oxidation number is the balance of protons and electrons in an equation, not quite. Okay? So let's try an easier question. The charge is the balance of protons and electrons. Oh crap, they're the same definition already. Charge is the balance of protons and electrons in anything. Everything. That includes elements. That includes molecules. That includes polyatomic ions. Everything has a charge. Okay? That is what charge is. It's the balance of whatever we're looking at. It's the balance of protons and electrons in that whole system. Well, what is the oxidation number then? Still a balance of protons and electrons.
How much it's able to give?
Nope.
In an individual species.
It's not even in an individual species, so that's getting better, because a species could still be a charge. H plus is a species. H2 is a species. If I look at the balance of protons and electrons in those species, in H2, it's 0. The balance is exactly the same. I have a charge. In H plus, it's +1. I don't have an electron. I have more protons than I have electrons.
So is it shared? Is it the change of...
No, it's not even shared charge. Shared charge still goes back to our charge. What is the oxidation number? It applies the balance of protons and electrons in an singular atom. When we look at the combination of those atoms to make molecules, we're now looking at the balance of protons and electrons and the combination of those to make the charge. But our oxidation number only applies to an atom. Okay? And that becomes a bit tricky because it's never directly given. We're only given the charge.
Oh,
Question?
I was just going to say, is it kind of like, well, maybe it's not even like...
Go ahead.
Like carbon has like 3 different, I think it's carbon 12, carbon 13. Or is that
So
completely
there's an
different?
interesting idea. Carbon 12, carbon 13. Where are those numbers written?
On the left side.
Upper left-hand corner. So is it the charge?
No.
No. So what is written in the upper left-hand corner? Protons. How many protons does a carbon atom have?
6.
6. Not typically. How many protons does carbon have?
Oh, 6.
6. Always 6. What the heck does 12 then mean? Or 13? It's the mass number. It's the number of protons and neutrons. Our upper right-hand corner is the number of protons and neutrons. Okay. Well, I'm looking at the balance of protons and electrons. That's going to be provided in the upper right-hand corner. That corner is reserved for charge. And that's going to be the sum of the protons and electrons. Okay. Well, how would I know how many protons were there?
Subtract.
It's protons plus electrons, right? Okay, equals that number. Well, that number, since there's nothing written there, is 0. How do I know how many protons or electrons are there? Could I have 12 electrons? Why not? If I had 12 electrons, that means I have 12 protons. And if we looked at our charge, that would become charge. Electrons are negatively charged. It would become 0. Doesn't that work?
Oh, yeah.
But there's neutrons in 0.
Do the neutrons contribute to charge?
No.
No.
Just a
But
little.
they take the
So could I have 12 electrons? No. Why not?
because it can have only 6 protons.
Say that again.
It can have 6 protons.
I can only have 6 protons for this. Why?
Because that's what carbon is.
That's what carbon is. The protons are defined as soon as we write down the element. Okay? As soon as we've now specified that, I know the number of protons. I also know the charge, because the charge is written where? The upper right-hand corner, which then allows me to determine the number of electrons. Okay? Doing that calculation. That's where all that information is embedded into our whole notation. Super exciting. I can tell. You guys are looking like, yeah, that was awesome. Okay? So, what can we do with this? So, what happens when we look at a reaction? Well, we could go through and identify the oxidation states. Okay? And interestingly enough, because we now know that oxidation states are the balance of protons and electrons for an individual atom, of course we can look at this and we'd say for zinc, its oxidation state is 0. Right? Everybody goes, yeah, absolutely, it's got to be 0. Somebody's got to challenge that. Really? You just look at that and you're like, yeah, that was totally 0.
I mean, it doesn't have to be 0, but
How would we know it's 0?
because it's a
There's
solid.
no charge.
There's no charge, but does the charge the same thing as oxidation state? No.
Protons is equal to neutrons.
It's not an aqueous solution, so it's not an ion, right?
Okay. What was our balance of protons and neutrons?
Protons and neutrons or
Protons and electrons, sorry.
0?
Okay, what did it define? If we look at the charge contribution from our protons and electrons.
If the protons and electrons are equal, it's 0.
Well, what did it define? Charge or oxidation state?
Oxidation. Oh, no, charge. Sorry.
What did we say the definition was? The sum of protons and the charge of our protons and electrons
It's a charge.
on an atom is the oxidation state. The sum of protons and electrons on anything
Is a charge.
is the charge. What is our anything for zinc?
A solid.
Okay, it is a solid. It's also just the atom. So what ends up happening?
It's the same thing.
The charge is the same thing as the oxidation state because there's nothing else with it. That is the unit. So I can determine the charge and thereby say that that is also related to the oxidation state. Okay? How about the next one? H plus.
The charge is
The charge is plus 1. Or is there any other thing attached to that H?
No.
Which then also means that charge is
The oxidation.
also the oxidation state. There's our plus 1.
Because
Okay? I would be flipping out too, because I'm a bit irritated with the slideshow. Okay? You barely understand oxidation state, and what do they immediately jump into?
oxidation and reduction.
Applying the oxidation state to different reactions. That's a bit of a leap. Okay? We haven't really defined oxidation state and how to find it. That makes it difficult to do this. What's your question?
Coefficient make any difference?
Does the coefficient change the balance of protons and electrons on the hydrogen? No. Okay? If I bring in the 2, let's just say I did, how many protons would be in this? 2. How many electrons would be there?
2.
What was the charge?
Oh, yeah.
It would be 0. The overall charge from that would be plus 2. So that 2 would have to carry through to everything. So when looking at the oxidation state, I don't care about the coefficients. Okay? So we now have some semblance of our oxidation states. Okay. What happens to the zinc in the course of this reaction? It goes from a 0 to a +2. Its oxidation state has increased. Okay. How does it increase? Could we change the number of protons?
No.
Why not?
Because then it'd be a different molecule.
It'd be a different atom. I can't change the number of protons to change its oxidation state. What can I change? The number of electrons. Okay. So what did I do to it to go from a 0 to a +2?
Lost 2 electrons.
I had to lose 2 electrons. Wait, I became bigger by losing something?
You're giving away.
Did it become bigger?
It becomes more
0 versus +2. Which is bigger? +2. How did I get bigger by losing something?
Because it had to be
What did I lose? Electrons. What are electrons?
negative.
Negatively charged. The mathematical symbol for loss is minus. If an electron is negatively charged, what have I done?
plus.
I've gained. Okay? I've increased the oxidation number. So as you've probably seen through this semester, minus signs are a real SOB, and you have to be careful with them. Okay? Because if you lose track of that minus sign, you take a number from making sense to now not making any sense. Okay? So to go from the 0 to the +2, I lost electrons. Okay? Well, science is infamous for saying, here's a process, oh, I lost electrons, and then saying, well, that's too many words. That's too many words, what do?
Short instead of word.
Right? I could shorten those words or
Oxidation.
invent a new one. What's the new one?
Oxidized.
Oxidation or oxidized. What happened to the H+? We went from a positive to a 0. We shrunk the oxidation numbers, or we
Added a
reduced them. Okay? And just because you said that, how did we reduce them?
added with electron. Like that.
If we add a proton, number one, that's not going to reduce it. That's going to make it more positive. What did we add?
Electron.
Electrons. By adding something, I got smaller. Wait, what? What am I adding?
A negative electron.
A negative charge. That's why it's going down. It's that charge on that negative thing that you have to watch out for. Okay? So what happened? We gained electrons. Okay? And we could keep with it as gaining of electrons, but we again invent a new term. This one, the term actually makes sense.
Reduction.
Reduction. What happened to the oxidation number?
It went down.
It went down, or it was reduced. Okay? So it's trying to come up with patterns and explanations that match those. Okay? So we've got our oxidized and our reduced within that. Oh. So still, instead of actually coming up with a definition within our slides yet, we immediately jump into the next step of this, which is
Oxidizing.
oxidizing agent. Okay, well, we saw oxidized, and oxidized meant losing electrons. So an oxidizing agent must mean that it
Loses.
Takes.
does what?
Anything that's reduced.
It gains electrons.
Um,
Wait, but didn't we say oxidized was losing electrons?
That's the agent.
It's the agent. The ing and the agent are causing something else to be oxidized. So if I am an oxidizing agent, I can cause Nick to be oxidized. If he is oxidized, what happened to me? I was reduced. Okay? That's why they're called redox. They're in partners. So if you see ing or agent, usually I just skip it. I'm just like, fine. You want to ask that question, deal with it. I'll deal with it later. Okay? It's a question of tiering backwards to figure out what each of those things mean. Okay? Going all the way back to your oxidation states, which would be nice if we had that definition to work with yet, which I thought was in here, and apparently not. So finally, it might be nice if we could now come up with a way to assign our oxidation numbers. So this is what almost every textbook goes through and lists. The elements in their elemental form have an oxidation number of 0. Okay. So what was the elemental form of zinc?
Solid.
Symbol, thank you, it was solid. Zn. Okay, what is the charge on Zn in its elemental state? What's written in the upper right-hand corner? Nothing, so it is 0. So the balance in protons and electrons in this species is identical. I have the exact same number of protons and electrons. Okay. How many atoms are in that? 1, which then means the oxidation number and the charge are the same. That's what that rule is trying to say. Instead of saying, well, there's some basic principles of what's happening with protons and electrons, memorize a rule. Okay, there you go. You can memorize a rule. Fine with that. Let's just accept it and move on. The oxidation number on a monatomic ion is the same as its charge. Okay. What is the ion form for zinc? What is the charge? 2 plus. How many atoms are in that ion form? 1. Which means they're the same. The oxidation number and the charge are identical. We invented a whole new rule that is exactly the same. It's still applying the balance of protons and electrons. Okay, fine. Let's accept that and come up with another rule. Nonmetals tend to have negative oxidation numbers, though some are positive in certain compounds and ions. Okay, so we're saying all of our nonmetals, our rightmost elements on our periodic table, are typically negative. Okay, why are they typically negative?
Because they have higher electronegativity.
They have a higher electronegativity. They're attracting electrons towards them. So typically when we put them into compounds, what do? They steal electrons from other atoms. Of course they're negative. Okay? Except under very particular circumstances. When might chlorine lose electrons? So chlorine, that's pretty darn close to the upper right-hand corner. When would chlorine lose electrons?
When it comes in contact with something that's more electronegative.
When it comes in contact with something more electronegative than them. So when they go through and start listing out exceptions, what are those exceptions in reference to? Bonding our element to something more electronegative than it. Or in the case of hydrogen, hydrogen is typically a +1, but then sometimes, or sorry, a -1, that should be a minus there. When bonded to a metal, that's also phrased horribly, okay? It is typically a +1 when we see it, because we typically see hydrogen in what kind of compounds? Covalent compounds, where hydrogen is then bound to another nonmetal. And where are our nonmetals relative to hydrogen? On our periodic table. To the extreme right, which means their electronegativities are all larger than hydrogen, which means when I bond hydrogen to one of those elements, what happens to it? The nonmetals take the electrons from hydrogen. So typically when I put hydrogen to a nonmetal, it becomes positively charged. What happens if I bond hydrogen to a metal? Why does it become negative? If we look at our electronegativity, hydrogen is more electronegative than all of our metals, which then means when I bond hydrogen to a metal, it takes electrons and it becomes negative. So it's looking again at the balance of protons and electrons in those. That rule is stuff we've already derived and seen before. There's nothing new there. Okay. We add an extra couple things on this. Fluorine always has a negative number, and it's stupid PC Mac confusions. Always has a negative number. Why would fluorine always have a negative number? No exceptions. Fluorine is the most electronegative element, meaning when I put fluorine next to anything else, what's it going to do? Always take those electrons. So fluorine will always be a -1. There's no exception to that. Okay. We might expect that chlorine, bromine, and iodine would follow suit because they're all in the same group. They do typically carry a negative charge, When would they not carry a negative charge?
Suppose the fluorine.
When they're bound to, say, fluorine. Why fluorine?
Because it's taking-
Fluorine is more electronegative than those elements. Okay? Typically, we see it pop up with oxygen. Okay? So our halogens will again carry a -1. Okay? They can be positive, typically when in oxyanions, or a fancy way of saying
an electronegative
oxy is,
oxygen.
they typically become positive when bound to oxygen. Why? Oxygen is the second most electronegative element on the periodic table. Okay? So these rules are really things that we should, in theory, already know and be applying. Okay? Whether that's obvious, that's a separate issue. Okay? And I'm not saying it's easy, but there's rules that we've already worked with. Yes?
So I was just thinking about, like, when you were saying that hydrogen can also be negative, doesn't it take ionization energy in order to make it negative, though?
So when we look at our ionization energy, when is ionization energy true? What is the ionization energy?
Isn't the amount of energy it takes to take away an electron, right?
Close, but not quite. Anybody know? It is the energy required to rip a single electron away from a single atom in the gas phase. What if you're not a single atom? Ionization energy is invalid. What if you're not in the gas phase? Ionization energy is invalid. Right? What do we use the ionization energy and its partner? What's the partner of ionization energy? Okay, electron affinity. We combine those two and we come up with a new term. What is that new term? Electronegativity. The ability of an atom to accept electrons from another atom, because you're now putting those two systems into a equilibration effectively. Okay. Rule 4, the sum of our oxidation numbers in a neutral compound is 0. What is the charge on sodium chloride? Upper right-hand corner, it is 0. If I add up all the oxidation numbers of the sodium and the chloride, what must it equal? Of course, we invented a new rule for that, because that's now a fascinatingly new thing. Okay. The sum of the oxidation numbers in a polyatomic ion is the charge on the ion. You mean to say that if I look at hydroxide, that negative charge, that if I look at the oxidation number for oxygen and hydrogen and I add that up, it magically gives me a negative charge, the charge on the ion? You mean the exact same thing you already said in the previous rule, which we already said was a redundant policy anyway? Yes, that's exactly right. Okay. These rule sets are very, very redundant. Okay. So here's what I would argue it boils down to. So now you're getting into my slides. You'll notice that my slide has pretty much everything on there. Okay, the rules that we just went through. I did include some exceptions for our oxygen, so I actually listed those exceptions. Peroxides, when we have oxygen bound to oxygen, we don't get a -2 oxidation state. It carries a -1. Why would it not be -2?
Because it's
What is the oxygen bound to? Oxygen. Which one's more electronegative? They're equal. So what does that mean they do with the electrons in that bond? They equally pull them, which means they share it. There's our -1. Right? Hydrogen, typically a +1 except when bound to metals. We did address that one. Our halides are -1 except when bound to oxygen. Okay, the one exception there is fluorine. Fluorine will always be a -1. Okay, will we ever see fluorine bound to oxygen? No, not really. It's not an easy compound to make. Okay, highly, highly reactive. Okay, so we don't have to worry about that. The big one on this is the one that we've kind of talked about. The sum of the oxidation numbers equals the charge on the molecule. Okay. How many of you are good at reading English? Really? Okay, you should have at least raised your hand for that. I was going to make it slightly more difficult. Okay. What I was going to make slightly more difficult is, can we translate the English into a mathematical expression? That is a harder step to do. But let's try and do that. What are we saying here? The sum of the oxidation numbers. So let's pick a difficult compound. If I take the oxidation number of chlorine and I add that to the oxidation number of oxygen, I should equal the charge. And where's the charge specified? Upper right-hand corner. So in this case, I would know that charge is a -1. Is this formula correct? It's the sum of the oxidation numbers for every atom in that formula. I should really be writing plus the oxidation number of oxygen, plus the oxidation number of oxygen, plus the oxidation number of oxygen. Because I have 4 oxygens. Now that equals -1. How many of you want to write that out? Okay, what's your shorthand?
4 times oxygen.
The oxidation number of chlorine plus 4 times the oxidation number of oxygen. Is it really 4?
We changed it to 3.
Okay, so the formula that we came up with to address that was too specific. How do I change my formula? I could change it to 3. Okay. You're still wrong.
So it needs to be
Cancel it out.
times
Cancel it out.
Times.
x or whatever.
What are you going to define x as? I like that.
The bottom, what's it called?
The number of molecules.
The number of oxygen atoms in that formula. We now have a formula, no matter how much of a dick I am changing the numbers, that will always work. Lovely. Okay, and then that will equal -1. Is our formula right? Why no?
Well, not the -1.
No, the -1 is still -1, right? There's still 2 oxygens, right? That still works.
We should still do the number of bromide ions.
Bromine ions. Okay. That's what you want to write? Okay.
The charge is still the same.
The charge is the same, but does the formula still work?
Yeah, because
That says the oxidation number of chlorine. Is that chlorine?
I didn't think you were being that specific.
Yes, we need to get specific and come up with a general formula that always works. That is the point of this. Using a system that works only half the time is a failing grade in the class. So what are we looking for? The number of our atom times the oxidation number of said atom plus the number of the atom times the oxidation number on our atom. Okay, and then that would then equal the overall charge. Of course, it could never be that easy, right? Mike's too much of a jerk for that. KMNO4. Does your formula work?
You could just add another.
Ah, okay. Our formula only works for 2 atoms. This only has, or this has 3. So what do we need? We could add 1 more. Okay. Some of you that I have taught are starting to remember. Plus, ... until we've covered all of our atoms. That then equals our overall charge.
You just factor out the total number of atoms in that whole thing, and then just do total number of
Can you factor out the atoms? It depends on how many atoms are there. You're going to not like factoring that.
No.
Well, I mean, each one is going to have the number of atoms times the oxidation number.
But is the number of atoms the same thing? It's a different atom each time. This is atom A, this is atom B, it's atom C, atom D. Okay, they aren't the same variable. Okay? It's the summation of them.
Number of atoms.
Okay? So, charge applies to a unit. Oxidation state applies to an element. Can everybody tell me the charge in the top questions? Starting with the first one on the left. It is?
0.
Next one. Next one. Next one. -2. Okay, good. You've got all that. So, because it's more difficult, I'm going to do the oxidation state one. Okay? For that first one, the number of the element. I think there's 1 copper there. The oxidation state, I always need to solve for it, so I'm going to say that's X. This must equal the overall charge. That's what my formula told me. Well, the charge is always given to me in the upper right-hand corner. It's 0. So X equals 0, and I said X was the oxidation state for copper. Cool. See? Really challenging. How about the next one? Well, that's a little different. So let me do that one too. Okay, so I have 1 copper and copper plus 2. I don't know its oxidation number, but I know the overall charge is plus 2. Oh, I can solve for this. I get X equals plus 2. The oxidation number, copper plus 2, is plus 2. Cool. What's the oxidation number in nitrate? Shut up. Just her. I didn't hear anybody else answer. What is the oxidation number in nitrate? We have an oxidation state that must apply to the atom. Can I explicitly look at nitrate and jump to the oxidation state? No, because multiple atoms. I have to go through and solve it. So the stuff that I did over here that you're like, why are you solving for? That's pretty stupid. That builds up to allow you to solve for your oxidation states here. Do you think you guys can do that one on your own?
Yes.
Okay. Do it. I'll give you 30 seconds. 5. Technically, both of those are wrong. Except, Nick, what did you say?
5 for N, and then -2 for O.
Specifying both, you're now right. Okay. There's 2 elements. You must specify the oxidation state for both elements. If you only specify one, you aren't specifying it appropriately. I don't know, is that +5 to the oxygen or the nitrogen? You have to be detailed. So when we go through and look at this, the number of nitrogen, how many nitrogens are there? 1 times the oxidation number. I don't know. Plus the number of oxygens. How many oxygens are there? 3 times the oxidation state of oxygen. Hold for a second. I need to solve for it. I don't know. This then must equal the charge. What is the charge on that compound? -1. I could pretty this up a little bit, and I'd get X plus 3Y equals -1. I have 1 equation, 2 unknowns. Those of you high up in our algebra, can we solve that? We need 2 equations to solve that. Is there a second equation that we're required to know?
What y equals is.
We are required to know that y equals -2. We're required to know that the oxidation state for oxygen is -2. You need to know that. As soon as you've got that memorized, you can now solve.
Can you find that from the table? The periodic table?
Ignore the periodic table. Really, just memorize it. Don't try and tie it back to the table. It's not that you're necessarily wrong. It's a separate system. If we go through and solve, x minus 6 equals -1, what do we get? X equals +5. What did I say x was? Don't tell me +5.
Oxidation number of
The oxidation number of nitrogen. Okay. Make sense? Okay. Do you guys need to do the sulfate? I saw a couple no's, so we're going to move on. But we can see all the answers. Whoa, sorry. There's your answers. Ta-da! Answers. Determining our oxidation states. Okay? So we could go through and now apply this to electrochemistry, looking at a reaction. What would we need to do for our oxidation states? Determine the oxidation state for...
All of them.
What do you mean all of them? What's all of them?
Both the reactions. I mean, both the reactants and products.
The reactants elements and the product elements. Why?
You don't need to worry about the It's supposed to be equal.
So you can figure out which ones were oxidized and reduced.
We're trying to identify if this was an electrochemistry reaction. Did our oxidation states change in the course of the reaction? Which means I have to calculate the oxidation state for every element on both sides of the equation. If all I'm trying to do is identify, is it a redox reaction, I just need to pick one element, hopefully, and get lucky. The oxidation state, oh God, that's a calculation I can't do in my head. 5. No, it's 5, isn't it?
Yeah.
There we go. That wasn't too bad. I'm not a complete idiot. Iodine equals plus 5. What does iodine equal in the product? 0. Did its oxidation state change? Yes. That means we're doing a redox reaction. That means we now need to apply all those big fancy extra words we were looking at. Our oxidized, our reduced, our agents, and all that fun stuff. Yes?
Now, as it's iodine, as it's never mind.
Okay.
I was going to say it's a solid, but never mind. Still,
It's not going to affect its oxidation state. Okay? So we could go through and do that. There we go. All solved out.
I have a question.
Okay. Everybody look at the back. Sorry, there were too many answers on the screen. Okay, go ahead.
The oxidation and the reaction is supposed to be equal to the oxidation number in the whole product.
Balancing charge we haven't even got to yet, but yes. Okay? So what do we have to do for this equation? We have to decide what happened, which means we need to look at the oxidation states for every single element all the way through it. Okay? And if we did that, which we already did one of those, we know iodine was a plus 5 in the reactant, and in the product it was a 0. What happened to it?
Lost electrons.
We went from a plus 5 to a 0, which means it gained electrons. It's that stupid minus sign messing with us. Okay. What happened to the oxygen? What is the oxidation state of oxygen? Negative 2. What is the oxidation state of oxygen? Negative 2. Did it change? Okay. So what occurred? Silence was not a bad answer. Didn't change. We didn't get a change. Okay. What happened to carbon? We kind of got a hint there. Started at a plus 2 and it became 4. Okay. To go from a plus 2 to a plus 4, I'm becoming more positive, which means I have to lose the negative charge thing. That's going to be losing electrons. This comes back to those definitions we were talking about earlier. Okay? Loss of electrons is not sciencey. Gain of electrons is not sciencey. So we invent a new word. Our word for gain of electrons was? Reduced. Our word for loss of electrons is? Oxidized. Yes, you had a question?
No.
Okay. So we could specify that information out. Okay. We look at it, we got LEO. Leo. What does Leo represent? Fair enough. Outside of a chemistry class. A lion. Leo. What do lions say? Grr, gain, electrons reduction. You have a mnemonic device that now combines all of that information. You don't have to memorize all these stupid words. Loss, electrons, oxidation, gain, electrons reduction. Leo says grr. Okay. Yes, I heard somebody shout out the others. 1. You may have also heard oxidation is loss. Loss of what? I don't know. It's not listed in my thing. Yeah, you can tell I don't like that one. Oxidation is lost. Whoa. Is oil rig the same kind of idea? Okay. I'm kind of an environmentalist. Oil rig, Leo. I'm going to stick with the lion. It's a little cooler. Okay? So, as long as you remember those, you're good. So you then have to be able to apply and look at a reaction and say what was oxidized, what was reduced, all of that fun jazz. Kind of make sense? Okay. So now we got to look at balancing these reactions. Okay. Balancing the reactions can exist at varying stages of difficulty. Okay? The method that is most consistent is going through and using what is known as the half reaction. Okay? What type of reactions were we looking at? Redox. And you always hear them referred to as redox, not just reduction or oxidation. Why?
Because they both reduction and oxidation.
To do a reduction reaction, I must do an oxidation. Okay? So when we write them out, we'll always see them written out together. Okay? But that doesn't necessarily make it easy to balance. So what we'll do is split them in half. Why is it in half? Well, what parts of a redox reaction are there? Well, there's the reduction, the first part, and the oxidation, the second part. There's two parts. So if I look at one of them, that's 1 out of 2 half reactions. Okay? So we are splitting those reactions, so we're treating them as their own reaction. They never can occur on their own, though. Okay? And that's what they're trying to say within this. So first thing we'll do, which you don't need to do, but whatever, assign an oxidation numbers to determine what was oxidized and what was reduced. Okay? Because then you can say, well, these were oxidized and these were reduced. And you can split it in that fashion. Okay? Write your oxidation and reduction half reactions. So by defining your oxidation numbers, you now know which one was oxidized, which one was reduced. Please reconnect. Okay. The next part is to balance each half reaction. Okay. What you should have learned in 151 only had part A, really. Balancing elements other than hydrogen and oxygen. Okay, that was it. Now that you're in 152, we add a layer of difficulty on top of this. We'll then move to balancing our oxygen. But we're going to balance our oxygen in a very particular fashion. We're going to do that by adding water to the appropriate side of the equation. So if I have a bunch of oxygens on the right, what do I need to add to the left? Water, with an equivalent amount of oxygens. What is the problem with adding water? You also add hydrogens. So we are fixing balancing our oxygens by adding water, but at the same time that we add the water, we create a new issue. We've now added excess hydrogens. So how do we balance the hydrogens? By adding H plus to
Balance the charge.
not balance the charge, the hydrogens on the other side of the equation. So we're going to be going back and forth when we try and set this up to solve. Okay? Make sense?
So if you put water on one side, you have to put hydrogen on the other.
If we put water on the left-hand side of the equation, what do we have to put on the right-hand side? How many?
2.
2 hydrogens, because every water molecule has 2 hydrogens in it. Kind of make sense?
Now we have to adjust it for every, so say you put like 4.
Every time it pops up, we have to worry about it, yes. Okay. The last thing we can do is balance the charge by adding electrons. So we can add up the charge of every species, figure out the charge on each side of the equation, and balance that by placing electrons into the reaction. Because we are doing 3D, guess what we don't need to do? Step 1. Okay. 3D and step 1 are identical to each other. It's just a question of when you want to address it. Okay. Then we can go through the fun parts that you should again be used to from 151. Multiply your half reactions by a whole number of integers so that your electrons gained and lost equal each other, because we don't want electrons left over in our reaction. Okay, why? How many of you have seen just an electron chilling, running around the room? Did you guys do that spectrograph lab where you had a little picture thing and you were looking at the lights? Yeah, some people vaguely remember that. Why did we have lights? Say that again? Electrons are going through it. What are we doing? We took a sample with our gas in it and we pumped a bunch of electrons in there. Okay, what happens when we pump a bunch of electrons in there? We scare the living bejesus out of the elements and they spit light out. Okay. Why? Electrons are stupidly high in energy, which means when they impact anything, they very violently react and jump to higher energy states. When they relax back down to the ground state, they emit that energy. they're emitting that energy as light in the case of those lamps. Okay? Electrons are incredibly unstable. We cannot produce them. We cannot just react them. They don't come from nowhere. That's why our redox reactions are always tied to each other. We must do the reduction and the oxidation at the same time. Kind of make sense? Okay. So, let's consider the reaction shown below. Okay, and I got to do a lot of erasing here and some addition of stuff. Well, I guess I didn't have to erase all that. See, we add permanganate slowly into our solution, and what happens? It turns pink. Neat. And now we can erase it all again. Okay, so we want to use our half reaction method. There's supposed to be an arrow in here. Officially, we're looking at equilibrium just because it's equilibrium. We want this reaction at the end. Okay. What was step 1?
Write down your oxidation states.
Write down your oxidation states. And I would argue that's more trouble than it's worth. Okay. What did this species become? What did our permanganate become? Did it become CO2? Why not? There's no manganese. Exactly right. So what did the permanganate become?
Manganese and
Manganese. That's it. There's no carbon and permanganate, which means it did not become CO2. So what's our first half reaction? MnO4. Oh, and it left off the charges. Anybody know the charge?
It's a negative.
Good. Becomes Mn plus 2. Okay. So we were supposed to split our half reactions, so let's split our half reactions. What's the other half reaction? C2O4 with what charge? Anybody know the charge on that one? It's a trickier. It's a -2. It's actually oxalate. Okay, this is a font shift issue. I apologize for that. And what does that become? CO2. Okay. Do you have a question?
No, I didn't know why the negative
charge.
But it was.
You'll also notice that I'm not a fan of the sign or the number then sign. I always do sign then number. Ultimately, it doesn't matter. So what was our next step? Now that we've got our half reactions. Okay, balance. So let's balance the first one. First step of balancing was anything other than oxygen and hydrogen, which would be, in this case, manganese. Is it balanced? Yes. Now what do we do? Now we balance our oxygen. Okay. Is the oxygen balanced in our red equation? No. So what do we need to do? We need to add water, and we'll add the water to which side? Product side. How much water do I need to add? Why 4? There's 4 oxygens on the left. Cool. Manganese is balanced. Oxygen is balanced. Good, we're done. Now I have to add H+. Where will I add the H+? Why to the reactant side? To balance out the hydrogen from our water. So I add H+. Well, I add 4 waters, so I've got 4 H+.
It's 8.
It's 8 because H2. Oh, remember we got to account for all of our pieces. Just test. You said you didn't remember single half reactions. So set me up. Okay. Now what's our step? Balance the electrons. Okay. Which is really balancing the charge. What is the charge on our reactant side?
7+.
Why 7+? I only see a +1 and a -1.
It's 8.
There's 8 of them again. It's our total charge on that side. So our total charge, I said that right, on the left is +7. What is our total charge on the right? All right, it is only a +2. Water doesn't have any charge. Okay. Is our charge balanced? No. So I need to add electrons to the proper side of the equation. Okay. Some people could pick it out and immediately jump right on it. Okay. I would argue with that negative charge getting in there, that negative sign, that can mess with you. So if you don't know, guess. Okay, I'm going to guess the right-hand side of the equation. I'm going to add an electron to the right-hand side of the equation. What does the charge become on the right-hand side of the equation now?
Plus 1.
It would become plus 1. Am I getting closer to or further from? Further from. What does that mean? I added the electron to the wrong side. I need to add it to the other side. I'm a little bit tight there, but we'll squeeze it in. Whoa.
I gotta remember this from last semester.
How many electrons do I need? 5. So that now the total electron or the total charge becomes, and I've balanced my charge. Okay. Remember that whole deciding what was oxidized, what was reduced? Okay. And I said we didn't have to do that step because we're doing this step. Well, did this step really actually tell us what it was? What happened in that top reaction? We gained electrons. How do we know we gained electrons? Electrons are a reactant. If we gain electrons, we are reduced. Avoid the ing. Okay. That means permanganate was reduced. That means permanganate is the oxidizing agent. It caused this one to be oxidized. Which then means when we balance this one out, where do we expect to see the electrons? And it better show up on the right-hand side, otherwise we screwed something up. And if we did, just go back and check it. Okay, so let's move to the next one. Where do we start? Carbon. Balance the carbon, or is there carbon balanced? We need 2 CO2. What do we do now? Balance the oxygen. It is balanced. Do I have to add water? Do I have to add any acid? No, I don't worry about it. Okay, I only go through to adding the water and the acid if I need to. If I don't need to, I don't worry about it. So there it is. Okay, what is the charge on the left? Charge on the right. Is it charge balanced? What do we need to do? Add 2 electrons. Okay, I'm going to add 2 electrons. Oh, that's right, because that would then make that a -4 to 0, and that's not right. So I need to add them to the other side. Yeah? Part of this is Chem 130. Adding the acid and the base stuff is not Chem 130. Okay, so now what? Now what do we do?
Figure out which one's agents.
We could already figure out, we've already specified our agents for the top one. We could do the same thing for the bottom one. Our goal was to do what? Balance the equation. Okay. Did I balance the equation? No, not yet. Okay, so what's the next step in balancing the equation? What's that? Okay, I add the 2 half reactions together. You guys had to say it that way, didn't you? Okay. It's going to take a little while. Electron. Yeah, I talked to myself. Do it. 4 minus 2. Mn plus 2. 4 H2O. Please don't write this, by the way. I'll suffer through it. You don't have to. Plus 2 electrons.
Does that mean it's wrong?
Yes. Okay. You guys have done the whole net ionic and all that fun stuff, right?
You've got
Okay, so do we have things that are similar on both sides? Yeah, the electrons showed up the same, so we could cancel those. So, stupid text underneath. Bring that over here. And this becomes 3 electrons. Nothing else shows up the same. So there we go, right? That's our equation. So to run this reaction, permanganate needs to pull 3 electrons from the air. And what did we say about electrons? They're not in the air. What does that mean about adding this up? Screwed up. Okay, we have to make sure that when we add these up, what happens to the electrons? They must cancel out. They cannot show up in the final equation, either as a reactant or as a product. So all of that work that you made me write out, thanks.
So you gotta write out the net ionic
No, we don't even need to do that. Our goal is to do what? Make sure what happens. What balances? The number of electrons. That's our focus. If we can get our electrons to balance out, everything else will fall into place. I produce 2 electrons. If I produce 2 electrons here, those electrons must be consumed up here. For that top reaction to occur, how many electrons do I need? 5. If I run this reaction once, do I produce enough electrons to let that one go? No. So I need to set it up by multiplying those equations so that I get the exact same number of electrons produced and the exact same number of electrons consumed. What is the common number between 2 and 5? 10. That is our smallest common multiple, which means that 5 needs to become a 10. How do I make that 5 10? I need to multiply that by 2. Okay? If I multiply that by 2, it becomes 10. Okay? What do I need to do to the 2 electrons? Multiply it by 5 and it becomes 10. Yeah. So now the electrons cancel, I add it up, it's all perfect.
You have to adjust the rest of the equation.
I have to multiply that through to everything else. This 8 needs to become 16. The 1 needs to become
2.
The 1 needs to become the 8 needs to become 4 needs to become 8. The 1 needs to become 5. The 2 needs to become 10. I shouldn't have erased everything. That was dumb. Oh well.
We couldn't multiply.
Our 10 electrons will cancel out. Sorry, go ahead.
We couldn't multiply the lower one by 5/2.
We can't run half reactions.
I'm supposed to be at
It's got to be whole numbers. Which then means I get 16H plus. Sorry, I got to turn around and actually read this. Plus 2MnO4 minus plus 5C2O4 minus 2 goes to 2Mn plus 2 plus 8H2O. Deep breath, right? 10 CO2 plus, oh, nope, that's it. And because this is general chemistry, what else should we be including in this?
Electrons.
Do we have electrons?
Or no?
The electrons canceled. What else should we be including in this?
Is there aqueous or
We should officially be including the phases. I will leave that to you and your instructor to decide if you need to write those. You might be able to guess my opinion. Okay? So, questions about that? Can we check our work?
Yes.
Yeah. How do we check our work?
Net ion equation.
We don't even need to do net ionic. We can just count elements on both sides and make sure they add up. Okay? I would argue it's easier than that. We shouldn't even look at the elements. We should be looking at the charge. What is the charge from our hydrogen?
16.
Charge from our permanganate? -2. Charge from our oxalate? This must equal +4. That's it, +4. So let's see, did it actually work? 16 minus 2 is 14 minus 10 plus 4, everything checks. Our equation is balanced. We could then theoretically be happy that we did all that work. Okay? What's a question that could be asked on the exam? What is the sum of the coefficients? Everybody know how to answer that? 16 plus 2 plus 5 plus 2 plus 8 plus 10? Okay. I'm not doing that, but that's what you could be asked. Okay? Make sense? Okay, so we're all happy with balancing acid-base reactions, right? Okay. So with that information, we balance this according to acidic conditions. What were our reaction called? They were acid base.
Oh, so we're using hydroxide too.
This is now only under acidic conditions. Could we have done this under basic conditions? Sorry, I didn't.
Maybe.
Yes. Yes, we could have done it under basic conditions. How do we switch it to becoming basic conditions?
Change H plus.
We need OH minus instead of H plus. How do we get OH minus into our equation? Starting over. And with that, I would leave. No, it's a little bit easier than just starting over. What do bases react with?
Hydroxide.
What do bases react with?
Oh. H3.
Acids. What is our symbol for an acid? H plus. Do I have H plus in here? How about I do an acid-base reaction and add OH minus? How much OH minus should I add? Why 16? I'm trying to react all the acid. But if I add 16 OH minus to the left, I'd better add 16 OH minus to the right.
In which case, would you need the hydrogen or no?
Would
you need the water or no?
What is 16H plus reacting with 16 OH minus? It is not 0. It's water. It's H2O. Just one? 16 of them. Did I do anything to the permanganate?
No.
Oh my God. Write faster. Feel free to start singing, just to fill the gap. 16 OH minus. Okay, and thank God I'm done with that.
No, it's H2O.
Why? What is wrong with it now?
H2O on both sides. So
There's H2O on both sides. God, are you seriously? Okay, fine. So I need to subtract. And H2O over there. Subtract.
Algebra.
H2O over there. And now, because I'm out of space, I'm going to go upwards. Okay. How many H2Os do I have? I now have 8 H2Os on the left-hand side. How many H2Os do I have on the right-hand side? I have
the other way around.
0. What else do I have on the right-hand side? 16 OH minus. Sweet mother of God. Now that I've done all this work, what do I now have to do? Negative 2 plus negative 10 equals negative 12. This equals plus 4 plus negative 16. This equals negative 12. Hallelujah! It's balanced. We now have our reaction under basic conditions. That's what you're dealing with when you're dealing with balancing half reactions under acidic and basic conditions. Does that make sense? Okay. That officially was all I needed to cover, so I'm kind of happy, and I'm even finished a minute early. Okay. Though I will say officially there were a bunch of other slides. So, hey, I actually kind of like that one. That's one of my slides. Right? That slide puts it all down on the exact same page. Right? So that's all the exact same rules that we just went through, balancing everything out. The one thing that kind of messed up is I don't have a step 6. What would the step 6 be? If we had to balance under basic conditions, what do we have to do at that point? Okay. That, I couldn't find my old slide on that, so I don't have it. The rest of this is then their step through on all of this. So you look at all that work. See, it's cool. And then we would get to, oh, look at that. That's all they wrote for balancing on a basic equation. What a load of nonsense. I actually showed all the work. That's all I had to do. Then dang, I would have just said that. Left you to deal with it. Officially, voltaic cells, I think now goes to you guys. I was told to get to it if I did. I didn't. So I think it now goes back to you guys for your lectures or for the coming weeks.